Chapter 3, I'll bring up the web page for the class here and point it out. So here we are. We've had the first couple classes, and people should hopefully be doing some projects. And so we're down to this cryptographic security lecture, and I'll demonstrate 106, the next project. I should mention, last time people brought up that there's a new version of the book. I was just talking to Anthony about it. I checked into it. The new version of the book just added a chapter on cryptocurrency, and that's not very important, so I wouldn't worry about it. We don't need the new version. Now, in a couple of years, they'll have a chapter on post-quantum cryptography, and that's important, but they don't have it yet. So we're not missing anything by using the old version, and if you did get the new version, that'll be fine too. It doesn't matter. Anyway, so let's take a look at this chapter. So here we go. Cryptographic security is you decide how strong your cryptography is. So you want it to be impossible for people to get in without the key. So you have to, but there's no such thing as impossible. So instead you have to determine a level of difficulty, and then you have to decide whether that level of difficulty is sufficient for your needs. So now informational security is theoretical impossibility, where even if someone had all the computers in the world and all the time in the world, they could never get in without the key. And that is what the one-time pad provides. The one-time pad is the only cryptographic system I'm aware of that is actually theoretically impossible to crack. And the reason is you have a different key for each letter. And so you have a series of letters in the encrypted message, and you can decrypt it into any series of letters that's the same length. So you can't tell which one is the right message. Every possible message will appear if you try every key. So you can never decrypt it. Even all the computers in the world won't get you any closer. You'll just have a ream of possible messages, and you have no way to know which one is the right one. But normally what you have for everything else is just computational security, where if you had an infinite amount of time to try every possible key, you would get in. And the only issue is you make it so that given the current speed of computers and the amount of money that you imagine your enemy has, they cannot practically get in. This is what you really settle for. So that's the point. That's informationally secure. If there's no way for anybody to ever get in, that's the one-time pad. But in practice, nobody uses the one-time pad, hardly ever, because of the key distribution problem. You have to deliver a random pad of keys that's equal to all the total messages you're ever going to send to the other end. And that means, megabytes or gigabytes of key, and that's just very difficult to do, so we use less secure ways of simulating it, like AES. AES, in many modes, just creates a pseudo-random bit, so it's a way of creating something that's close to that one-time pad. It's a pseudo-random pad, but it does have some patterns, because it wasn't completely random. It was generated from mathematical operation on the key. Let me just check for comments in the Twitch. There are none. Okay. All right. So AES 128 is computationally secure because you'd have to try all possible keys, and that's 2 to the 128, and that is more than all the computers in the world could do in all the time in the universe. That's a really big number. And so now our quantum computers, however, can try them 2 to the 64 at a time. So if we had a working quantum computer with probably a lot of qubits, like millions or billions, and those qubits were very high quality, then in principle, you could get in with only 2 to the 64 operations. Therefore, AES 128 might be broken if quantum computers advance very far from where they are, so realistically in several decades. So if that happens, AES 128 will cease being computationally secure, and then we'll just move to AES 256. When they approved AES 128, they made another version longer just for this reason, saying, 128 should be enough, but in case you need more security, we'll have a longer version. And if an AES 256 would still remain secure even with the ideal quantum computer, because they would have to do 2 to the 128 operations on the quantum computer. So that's why AES is not really being destroyed by the onset of quantum computers. All that we'll have to do is switch to the longer key. So you can define security this way. It's for T and epsilon. T is the number of calculations, and epsilon is the probability of success. So if there's no faster way to crack AES 128 than guessing the key, then you have T, or T over 2 to the 128. So if you make one guess, you have 1 over 2 to the 128 chance of getting in. If you could guess 2 to the 128 guesses, then you'd get in for sure. That's all this is saying, and a little funny way to say it. So try one key, that's your probability of success. If you can do 2 to the 64 keys, then you have the probability of success is 1 over 2 to the 64, which is still very small. But if you could actually try all 228 keys, then you would get in probability of success as 1. So that's what it means. And that's why you can rate the quality of a cryptographic system by how many bits of security there are. How many guesses would you have to make to have something approximately 100% chance of getting in? So that's how you quantify it. So a perfect cipher with a 128-bit key provides 128 bits of security. Now the issue is there a shortcut? Is there some way to not really try all the keys? That's a defect in your algorithm. And if that happens, then of course, even if you have a 128-bit key, you don't really have 128 bits of security because you don't really have to try them all. And this has happened a few times when we have defective systems, like WEP. Wired Equivalent Privacy was the first encryption scheme used for wireless networks, and it had a 104-bit key. Now that should have been fine. 2 to the 104, anything over 100 is effectively unbreakable. 2 to the 100 is a number beyond what we could ever do with all the computers and all the time in the world. But the problem is there were ways to get in without trying all the keys. In 2001, they found an attack that would get in with only 2 to the 20 keys, which is a whole lot less. This is only 1,000,000, so any computer can do that. And they found another attack later that could get in with 2 to the 15 keys, so this is just very badly broken. And because the cryptographic algorithm wasn't very good, you didn't really have to try all the keys. And there was a relationship between packets you could use to exclude whole bunches of keys, and then you only had to try the remaining keys. So the substitution cipher is another one. If you think about the substitution cipher, you replace A with another letter, then you replace B with another letter. The number of key space, you have 26 possible ways to replace the first letter, 25 to replace the second letter, 24. This is 26 factorial. That's 2 to the 88. That's pretty good. That's almost 2 to 100. So you would think the substitution cipher where you replace every letter with another letter would be uncrackable. But the problem is there is a fast way to crack it. And when I was a kid, you were in the Sunday newspaper. You'd have cartoons and a encrypted thing, and kids would just break them. 6-year-old kids would just break them for fun. Because what you do is you look and find a one-letter word. Well, that's got to be A or I. Then you find something like this with an apostrophe, and this must be, you can probably figure out what that is. Here's one with an apostrophe Z. That's probably a T or an S. This is probably the word can't. I can't is how I would guess. You just guess a couple of words, then you fill in the missing letters, and you can guess the other words, and it actually is pretty easy to crack. Even though in principle there's 2 to the 88 possible substitutions, you can use the structure of the words and also the idea of the cartoon. It gives you some clue what's going on. It's actually not that difficult to crack. Made a couple of them. I'm not going to bother doing them, but if you've never seen them, you can try doing these, and they're all pretty easy to do. That's what you do. You start from a single word, and then you know that's an I or an A. Then you fill that in everywhere, then you find something with another small letter word. So, you know, one of these is A and the other one is I. So it doesn't take long. And therefore, even though it has a key space of 2 to the 88, it is not give you 2 to the 88 security at all. It's much easier to crack than having to guess 2 to the 88 keys. Let me try the, okay, no comments. All right, so RSA 2048. This is what's currently recommended to be used, although they're saying within the next few years we should go up to 3072, I think. So the key is 2048 bits long. And this confused me a lot when I started doing cryptography. Why is that key so long? That seems really ridiculous. But the thing is, RSA keys are not just random numbers. They are the product of 2 random primes. So you can't really choose all the bits arbitrarily. So this only gives you 112 bits of security, which another way to look at it is less than 100 bits. Another way to look at it. And the point is, this is considered good enough because it's around 100 bits of security. But this is why RSA has fallen into disfavor. The fact that it's 2048 bits long means it takes a lot of CPU to calculate. And ECC, elliptic curve cryptography, which we'll get to, does public key cryptography with much shorter keys. So it's much cheaper. It takes about 1/20th the computation time to encrypt with ECC to get the same level of security. RSA was just the first algorithm that was developed. Elliptic curves came later, and they're more efficient. All right, so here's the recommended from the government from a few years ago, telling you if you want 112 bits of security, you need 2048-bit keys, 128, you need 3072, and so on. And so, you know, anything above 100 is essentially unbreakable. And for the military, they usually try to go twice as far, just to make sure you have a nice buffer, so that even if somebody finds a defect in the system, you'll probably still be okay. And so up through 2030, this is considered acceptable. after 2031, they want us to move up to 3072. And this is because they're worried about the improvement of attacks coming from quantum computers. and really, now, just this year, they have begun approving the new quantum algorithms. And we all should be switching to them over the next 5 or 10 years. Because it's all theoretical. I mean, the quantum computers right now are ridiculous. The only number that had ever been, a quantum computer could factor the product of two prime numbers into their prime factors. But on current hardware, the only case I know that has been done is they were able to factor 35 and show that it was 5 times 7. That's a long way from a 2048-bit RSA key. They need the hardware to get a million times better. But in 20 or 30 years, that might happen. Right now, the hardware for quantum computers is very expensive, very noisy. So you really can't get much done on a quantum computer yet. But they are getting better all the time. So the NSA is concerned that they will get really good quantum computers in 30 or 40 years, and therefore we should be encrypting our stuff with better algorithms, because you might, it's probably not okay if your data is decrypted in 30 or 40 years. Now, for some things, like credit card transactions, it wouldn't really matter, I suppose, because 7 years is the statute of limitations for any issue of fraud or taxation or anything. But for other things like medical records, it might not be okay in 100 years. You might have a disease, and your children might inherit the disease, and you might not want everybody knowing that. So that's why we should be switching to stronger encryption, over the next 5 or 10 years as they approve the algorithms. They've been working for several years to develop the best algorithms and approve them. And they've just released a few of them this year. There are a few more coming next year. And that's why I say the textbook update should come in about 2 years. Then it'll have probably 2 or 3 more chapters about quantum algorithms, and that's logical. Then a lot of the algorithms in that book will be on the way out, and the quantum algorithms will be coming in to replace them. All right, so you can, like other attempts to measure your cost, does it go on parallel computers? How much memory does it take? Is there a way to do a time-memory trade-off by pre-computing part of it and numbers of targets? So parallelism, if you're going to do 2 to the 56 sequential steps, that's bad, but if you were able to make them independent, then you could run them on something like a GPU. GPUs have a vast number of processors. So I'm not quite sure how many in a processor. I think it's a lot. It's like 1 per pixel. So you could just break this up into separate chunks on every processor, and they all run at once. That's why it gets much better. So if you have a multi-processing unit like a GPU, you can get a considerable improvement as long as the calculations can be performed independently. You don't really have to do step 1 before you do step 2. And for cracking a key by brute force, it's perfect for this. You just break the key space and say, this processor try these keys, this processor try those keys. They don't need to trade data between the processors at all. So it parallelizes very well. Then there's memory. There are some algorithms that are designed to require a lot of memory, not necessarily a lot of CPU time. See, Bitcoin uses SHA-256 hashing, and that is a CPU-intensive task, but not a memory-hard task, and that turned out to be a design flaw. The original plan of Bitcoin was to make money that nobody could control. They wanted to make money that no government could devalue and no government could outlaw. So they wanted to make it so there'd be a lot of people all over the world contributing to Bitcoin mining, and nobody could ever get a monopoly on Bitcoin mining, because then they would control it. But because they designed it so the only limitation is how fast your processor is for mining, then it turned out that what you had to do was buy a bunch of ASICs, application-specific integrated circuits, that were specialized just to do Bitcoin mining, and then you had to find a place that had the most electricity for cheap. And the power was the cost. And it turned out for a long time, China had a corrupt system where you could bribe the power company to get free electricity, massive amounts. So there was a period of time when something like 80% of all the Bitcoins were mined in China, because it was only, and the way Bitcoin mining works is it's a race. Every 10 minutes, people are trying to mine a block, and whoever gets it first gets a prize, and everybody else gets nothing. So if you have the fastest computer, you win the race, and everybody with slower computers almost never wins the race. So it's all about making the fastest computer you can possibly make. And that turned out to concentrate it in just one country. So that failed the fundamental plan of Bitcoin mining. Now, as far as we know, China did not manipulate the Bitcoin blockchain, but they could have. If China had passed a law and forced all their miners to obey the government edicts, which they certainly could have, they could have modified the blockchain dishonestly and stolen Bitcoin. Now, what they did instead was they outlawed Bitcoin. The Chinese government said, this is garbage, this cryptocurrency is not accomplishing anything, it's using all this power. You should do something that makes sense, like raise food or build phones or something like that. They said, we don't think this is productive, we're not going to have it here, and they outlawed it. Now it's mostly done here. But anyway, in both cases, it didn't really achieve its fundamental design goal of making a system that would be sort of democratically dispersed around the whole world, so no one nation or no one group of people could ever get too much power. But Ethereum tried to fix that. Ethereum used a different system called memory hard, so you needed a lot of RAM to go. Although Ethereum now moved to proof of stake, so they switched from this whole system where you have a bunch of miners competing. Now you just have to you just have to invest some money, showing you have a large amount of money invested in Ethereum and put it like on reserve, and then you get the right to participate in lotteries to do the mining. So that's what they've switched to, and that seems to work. Yeah.
What's the meaning of mining? What are you actually doing when you're mining the web?
What you're doing is everybody is spending their Bitcoin. You have Bitcoin is just a series of account numbers and the amount of Bitcoin. So if you give somebody Bitcoin, it goes from your account to their account. That's a transaction. So everybody's doing transactions. You gather all the transactions, and every 10 minutes you make a block. And you just choose some of them, put them in a block, and now you want to calculate the hash of that block. And you want to make that hash start with a certain number of zeros. So you can change a nonce number, you can change a random number, and hit all the rest of the transactions, calculate the hash, and just to make it difficult, you can't just attach the hash, you have to keep changing the random number until you find a hash that starts with a certain number of zeros. And last time I looked, it was 56 zeros. So you have only one chance in 2 to the 56 of doing that. And there's no way to predict it, so you have to just try random numbers until you're lucky and you get a hash that starts with 56 zeros. That's what mining a block is. And the point is, then you tell all the other miners, they all have to agree, then you get a prize. When you mine a block, you get to include a transaction giving yourself some money. You win an award. And if your block is approved, it gets added to the blockchain permanently. And everybody moves on to the next block. That's how it works. So it amounts to essentially a lottery. Everybody's printing lottery tickets, but if you have a faster computer, you print more tickets, you're more likely to win.
I still don't understand how it can make sense from an economic point of view, because the economic point is that you have to create value.
Well, yeah,
it doesn't seem to me that.
No, it fits the system called Austrian economics, which in Austrian economics, they say, for example, you had the gold standard, and the only reason gold worked is because there's only so much gold, and it's really hard to find more, and this is better than gold. This is a mathematical currency which cannot be forged, and you can't make more of it. The original system was you start with a certain amount of Bitcoins, and then every time you mine a block, you get an award, but the mining reward decreases with time. Every 4 years, the mining reward cuts in half. So there are only 21 million Bitcoins, and there can never be more.
So basically, the Bitcoin is a standard. We have adopted a standard.
Yeah, it's a way to keep track of who owns it, and it is a scarce resource. You can't ever print more, so that's what they said. It's better than gold as a medium of exchange. It means all it has is scarcity, and also it escapes all government control and regulation. You can use it in any country. Nobody can stop you. Unless you could shut down all the miners in the world, you can't stop it from going. Every 10 minutes, there's another block. So it was designed by people that wanted to develop money for the internet, and they also wanted to escape government regulation. It was developed because in 2008 there was a financial crisis in the UK, and the government devalued the pound. And the developers of cryptocurrency at that time were very, very angry about that. They were sort of libertarians. They said, we should have something like the gold standard where the government cannot control the price. And this would be the perfect standard, better than gold. According to the Austrian economic theory, this would be the perfect money. Because what you want is something that can't be forged and can't be stolen. And this effectively accomplishes that. There is this ledger that is cryptographically clean of who has everything. And you can never modify it because there are thousands of copies of it all over the world. So you can't fool anybody. It's clear who owns it at all times, and there's no way to forge Bitcoins. So that's essentially the perfect money.
So then the transactions themselves are just I mean, there are people who sell and buy
Yeah.
using cryptocurrencies.
Yeah, you can
It
do
seems
that.
to me, from what you are saying,
Yeah.
is that the raison d'être of the Bitcoin is simply to be exchanged.
Yes.
Because by being exchanged,
Well,
is that this value,
well,
the
now,
transactions happen.
well, actually, this is an interesting issue, and I used to have lectures about this when cryptocurrency is a big part of this course. There are four possible reasons for Bitcoin, and arguably it failed at all of them. You could say if you want it to be gold, you might be a medium of exchange, it might be a store of value, it might be a hedge against inflation, and it might be escaping government control by being distributed. It tried to accomplish all those things. Arguably, it didn't do any of them very well. Um, it turns out that the fees for doing a transaction rose very high. So it's not very practical. You can't. The fees are like $30 or $40 per transaction, so you can't use it for small purchases. And as a store of value, if the Austrian economic model was right, it would be independent of inflation, but that didn't happen. When there was inflation, Bitcoin price just changed too. So I'd say Bitcoin you could see as an economic experiment, and what it proved is that the Austrian economic model is wrong, and the Keynesian economic model is right. And Keynes said, see, the Austrian economic model is based on physics. You have so much money and so many goods. It's like water. So if you have more money and the same amount of goods, then it'll dilute it, and the money will be worth less. Okay, that's not what happens. Consider the economic crash in America in 2009. There was bank corruption about housing loans, so all the banks made bad loans and they lost their money and they were all collapsing. And Obama was president. And the old-fashioned rule was you just have to let the banks collapse because you can't just print money out of nothing and give it to them. That would just dilute the money and make the money worthless. But Obama didn't do that. He printed trillions of dollars and just gave it to the banks, who basically just stole it. And he gave it to companies just so they could pay the bills. And then, in fact, what happened is, this is Keynesian theory, said money is not like air. It's not like there's only so much it's smearing out. It's like happiness. It's like if the people are happy, then they go to work and spend money and everything's fine. If the people are miserable, they all hide at home and stick their money under the mattress and don't spend money and everybody goes broke. It's just like a mood. So if the economy is stopping, you just have to start it up again. So he just printed a bunch of money and gave it to them. And the result was it revived the economy. The economy came back up. In fact, some of those companies even paid back the money. They made more money. So apparently it justified the Keynesian model. And therefore, Bitcoin is not really necessary. It would be the perfect thing if it really was Austrian economics. But it appears that the world does not work that way.
Well, I would claim that it's not so much that the Keynesian model is useful, but that in today's world, the economy really needs circulation of goods.
It does. Well, that's the idea.
The faster goods travel, circulate, the more wealth you produce.
Exactly. But you have to stimulate. That's what Obama said. He said we just need to stimulate the economy to keep it moving, and that will be better. And he was right. But the economists at that time did not have a theory to understand that. The theory said that would be the wrong thing to do. And I think they're still arguing about why this happens. I think economics is not really that much of a science yet. People are still kind of guessing. It's like, they try. It's really important to make good economic decisions. And by the way, Biden is incredibly successful. We had another financial crisis caused by COVID, and everyone said we were going to have a recession because inflation rose high. And in the past, the only way to stop inflation is to raise the interest rate until you have a big recession. And they said if you could do it just right, you'd have a smooth landing. You'd smoothly go from 10% interest rate down to 2% without a recession. That has never been done, and Biden did it. He gets no credit for it, but he really accomplished like an economic miracle there. So maybe our current economists are beginning to understand how to do it better. But it is kind of a guessing game. And anyway, that's the theory of Bitcoin. And so Bitcoin is still around, but a lot of people say here's another, someone points out a good thing. One thing about Bitcoin, it's not backed by a government or military. Like you say, why is the dollar worth anything? Because the U.S. government is powerful, and they back it. And Bitcoin is not backed by anything except sort of by mathematics. And so, but that turns out to be pretty successful. Bitcoin keeps rising in value. It doesn't fall to zero. And basically the reason is crime. I mean, why did anybody use cryptocurrency? The answer is because they can't use normal money, and the answer is because they're doing something illegal. It basically are all doing money laundering. You're either buying something illegal, or you're hiding from taxes, or you're trying to escape your local currency. Like in Argentina, the inflation rate is like 100% a year. So the local currency is useless. It's illegal to use other currencies, but people put their money in Bitcoin because even though it has a lot of variation, it doesn't have an inflation rate like that. But that's essentially money laundering too. So it turns out that Bitcoin is useful for a large part of the economy that is more or less illegal and can't use the other economy. That turns out to be enough to make its value keep going up. It has a real pattern. Bitcoin goes up every year, then it crashes for 2 years, then it goes up higher for a year and back for 2 years. So there's a bunch of companies just, if you're willing to hold on to it for a long time, Bitcoin is not a bad investment, apparently. I'm not necessarily recommending it though, because fundamentally, as Jer here points out, it's not worth anything. If you had gold, at least you could make jewelry out of it or something.
Right.
If you have a bunch of Bitcoin, there isn't any obvious reason that it doesn't just fall to value zero at any time. But in practice, it doesn't. And I think that's because there's just a lot of need for illegal transactions. That's basically what holds it up. But it's very interesting, you know. And anyway, and the mathematics and the cryptography of cryptocurrency is very advanced and very good. And it's worth studying, and I used to cover it in this class and have projects about it, but right now it's kind of out of fashion, so I'm not planning to talk about it a whole lot in this class, but there are the optional cryptocurrency projects if you want to try.
The presentation that you were giving at the beginning of this class, right?
Yeah, I think I had some of it there, yeah, and and there's a whole bunch of projects. We set up our own mining and everything in a whole bunch of cryptocurrency because I'm pretty deeply into it. But anyway, and it may come back, but right now it's pretty much out of vogue. So anyway, we were talking about somehow it would take a lot of memory, and that's what Ethereum mining did, back when Ethereum was based on mining. Pre-computation is another way. This is time-memory trade-off. This was used to crack Windows passwords in the time of Windows XP. You would pre-calculate some of the calculations and store it in memory. And then instead of doing the calculations to guess each password, you would look up part of it by the lookup table. So by using more memory, you can use less CPU time. That's time-memory trade-off. And that turned out to be, because Microsoft used an incredibly weak password hashing algorithm that was designed in the 70s for like IBM, you could actually crack Windows XP passwords in about 5 minutes. Because there weren't very many passwords you had to guess. For example, Windows XP passwords broke your password into groups of 7 characters. If you used more than 14 characters, it just ignored all the ones after 14. You had 2 groups of 7, turned all the lowercase to uppercase. So there were really not that many possible passwords at all. And you could try them all in about 5 minutes on a modern machine by using a time-memory trade-off system. So, yeah.
You said that this is more CPU less time or more RAM less time?
More RAM less time.
More RAM.
Yeah. More RAM and CPU. It's time-memory trade-off. You could use more time or more memory. And so what happened is RAM got bigger and cheaper. And so there came a time when people had like 2 or 4 gigs of RAM, and you could put a rainbow table, they called it, in RAM, that would be like half a gig, which would be enough to make your calculation of each password very fast. So then you could try all the possible passwords because they're only 7 letters long. And they only have a small character set, like 36 characters, so there aren't really that many. And so you can crack Windows password hashes here. Here's the modern ones. If you look here, the LM hash starting with AAD, that was the old one I described that was used by Windows XP, and they no longer use it in modern versions of Windows. They just have a meaningless placeholder there. The NT hash is the modern system, which came out in 1993, and that is 1 round of MD4, which is very, very weak. Now it's only 1,000,000 times weaker than Linux password hashes. It used to be much weaker than that. This is Microsoft upgrade in 1993 was to switch to 1 round of MD4 and to not change the lowercase to uppercase and not have a maximum length. So it's harder to crack, but still extremely easy to crack compared to modern hashes like Linux or the Mac. And in fact, what you can do, if you want to crack a Windows password, you can extract the password with a hacking tool like Kane Enable is one of them. There's a bunch of them. And once you have the hash, you can just Google it because there's no salt. If I have a password and somebody else has the same password, we have exactly the same hash. So ever since 1993, people have been calculating tables and putting them on the internet. So all the common passwords are just on the internet. If you just Google the hash, you'll find it. It's ridiculous. And there are online free hacking stations like this one, Hash Killer, where you'll just find things. So you can just put in a hash, like this one here. I put in the hash and it found out it's Apple 9. So now, if you really had like 20 random characters, you wouldn't be able to crack it. But if you have any kind of password that people have used before and put on the internet, you can just look it up. So now this is not true of better systems. All right, anyway. So, and there's another thing. Suppose you have more than one password hash to crack. Suppose you're cracking into like a company and you get on their domain controller and they have 1,000 employees. Well, then you can try to get any of those 1,000 hashes, and therefore, in principle, you only have to make 1/1,000th as many guesses before one of them will hit. So that's another way to look at it. So you can evaluate your levels. Typically, there's only 2 levels you care about. 128 bits is effectively uncrackable, and if you want high security, you double that to 256. This is typically what you want. So if you're an ordinary consumer doing financial things, 128 bits is good enough. If you're doing the military or something super important, you use 256, and that's considered enough for a foreseeable future. So there's no real reason to have anything other than these levels. All right, so let's try. Yeah, but of course, something might happen in the world of mathematics or computing, but as far as anybody can tell, we're not going to crack 256 bits ever, centuries. So if you encrypt it up to 256 bits of security, there's no real reason to bother doing anything more. That's made it as secure as it's going to get. And of course, remember, cryptography doesn't mean nobody can get in. It just means they get in another way. All they have to do is sneak in and put a camera and look at your screen, or bribe somebody to tell them, or break into the safe and steal the secret. You know, cryptography only protects it in transit, or at a certain point. But somewhere, somebody's reading that data in plain text, and they could just get it that way. So
let's assume for a moment that we don't have any of these, how do you call this, side channel information.
Right. Yeah, that's the idea. If you don't have any of that, then cryptography can protect your data until it gets decrypted by someone with the key.
Right. But did I understand correctly that the goal of a cryptographer, so I'm creating the cryptography.
Yeah.
My goal should be to encrypt the message in such a way that the only possible technique to be used is the brute force. Is that my goal?
Yeah, you're right.
Correctly?
Yeah, I think you're right. You want the algorithm to be so good that there is no shortcut.
And
that's right. The best you can ever get is brute force. Like if you have a 128-bit key, you could never have more than 128 bits of security, but you might have less. That's right. That's if your algorithm is perfect, you will get the full 128 bits of security from your 128-bit key.
So if it is perfect, only the brute force would work.
That's right.
But it takes an infinity, but then
that's the idea. Then you just have to rethink. That's right. But sometimes, like I say, your algorithm is not so good. Like when you have 104 bits of WEP, you really only have 20 bits of security, which they did not know, but they found out because the algorithm had a flaw. And that, of course, you can't predict. Mathematicians are always finding new tricks, so it might be that the system that appears perfect today, which would be like AES, turns out to have a flaw. But nobody's found the flaw yet, but you don't know that they will never find a flaw.
Even here, I know.
Yeah.
If these are mathematicians that are developing these proofs,
how
is it possible that the proof has a flaw?
Oh, because
It means that these are not mathematical proofs, so these are statistical proofs.
No, they're mathematical proofs. So what you do is you analyze them with the tools available. For example, when they developed SHA, the secure hash algorithm, there was a technique that was not publicly known, but was known only by the NSA, called differential analysis. And what you did was you would hash two things that were almost identical. Mm-hmm. You would change just like one bit. And then only a couple of bits in the hash would change, and you could use that to reverse it. But nobody had thought of this in the public world yet. The national security secret world knew it. So when they proposed SHA-0, the NSA came out and said, no, change it to this, and they wouldn't say why. And it came out 20 years later people learned that there was a technique that cracked SHA-0 which they hadn't been aware of. And so that's the point. There's an endless mathematical cleverness. You know, you use the best techniques you have to crack it, and then when nobody can get in, you say, well, it appears to be secure. But you don't know that there isn't a smarter mathematician somewhere that found another way in.
So, okay, so, but we are not talking in terms of logical proofs. The type of proofs that mathematicians
No, I mean,
would
well,
give.
that's right. That would be the perfect. That was way back here. I mean, you could have informationally secure cryptography, and that means there is no possible way in ever. But the only thing that gives you that is the one-time pad.
Yeah.
All the rest of these have a short key, and therefore there is some pattern in the output. So in principle, there might be some way to exploit that pattern and get in. And you use more and more scrambling tricks to make it harder to find the pattern, but you never know you've really hidden it well enough. That's why fundamentally, one thing Bruce Steyer said, security through obscurity is all we have. We don't really have a barrier that cannot be breached. We just have a way of making it difficult to where nobody knows how to do it yet. But there might be some mathematical technique where you get in without knowing all the keys and without trying all the keys. That in principle can happen at any time.
Okay, but now I think it's clear.
Yeah, that's the idea. And that's why when I first learned this, I thought, well, good cryptography, it's perfect. But it's not that way. It's just strong enough to withstand the currently known attacks.
Yeah,
that's all you ever get.
But these are still empirical tests.
Exactly. Because just like people might build a better computer, they might develop a better math, and how do you know? That wouldn't happen.
But that's why I'm saying these are these are a sort of statistical tests, non-mathematical.
Yeah,
they must have some error.
Yeah, I mean, the point is, saying, can anybody get in is not a defined mathematical problem. You have to say, can they get in by using this procedure? Then you can answer that.
Yeah.
But this is why mathematicians like to prove, does a solution exist? That's a hard problem. Will this algorithm work? You can do, but all possible solutions, deciding if any of them will get in, that's like fundamentally almost philosophy at that point.
No, I understand.
Yeah, that's important. Let's try a Kahoot here. Good. The questions are very good. They keep things interesting.
No, because one contention that I have, and usually.
Mm-hmm. Yeah, got to turn on that machine there, so it'll be a minute getting in, but it's fine. We're not in a hurry. Got plenty of time. Oh yeah, I'll get the key up here. There it is. This is actually a fundamental thing about all security, is that everything is a whole lot less secure than we would like it to be. Like people tend to get sort of paranoid when they begin to realize you think you have passwords and encryption and everything, but none of that is really as good as you might think.
So my contention is that the contention that I found is I don't know if I'm right. Probably this is a little bit of speculation, but I think that the source of confusion is that the author seems to me that he confuses deductive approach with inductive approach.
Oh yes.
Logical mathematical
Yeah.
approach that proves the logical proof versus an empirical proof.
Yeah. It's really engineering. It's really just empirical.
It's just empirical.
Yeah, there are no actual fundamental principles that make our cryptography strong. Unless you had the one-time pad, there's nothing very fundamental here at all. It's just engineering.
Because what I tell students is that you need to understand the difference between deductive logic and inductive logic.
Yeah.
Because the rules are the same, but the value is different.
That's right.
For example, in deductive logic, we can say
Start from something absolute truth. You make an axiom and then you derive things from it.
right, but actually I make it more straightforward,
Yeah.
more pointed. Let's say in deductive logic, the affirmation of the antecedent is valuable. Because
Yeah.
say, yeah, if it rains, I will bring the umbrella with me.
Yeah.
It's raining,
Yeah.
then the consequence, the final conclusion is that I
Yeah.
bring the umbrella with me. However, you cannot see outside,
That's right.
but you see me with the umbrella.
That's right.
You cannot conclude from a deductive point of
That's
view
right.
that it's raining.
That's right.
However, because it's a fallacy.
That's right. But in the real world, nothing is ever that clean.
But that's what I'm saying.
Yeah.
However, from a scientific point of view,
Yeah.
from an empirical, inductive point of view,
Yeah.
the conclusion is more valid, is more
That's right.
plausible.
That's right.
So that's the difference between logical closures and statistical generalizability. I would say.
It is. It is. And in terms of this class, it's the difference between these two things. Informationally secure and computational security.
That is the
Informational
right
security would mean real strong fundamental principles.
logical.
And this just means practical by current terms. Yeah, very good. All right, let's try some of these here. Good. All right, so how secure is AES 128? The most common one we're all using. That's computationally secure. As far as we know, nobody can get in without the key, with current techniques and current hardware. All right, what kind of security does not change as technology improves? Yeah, that's the one. Informationally secure would be really fundamentally secure from first principles. Doesn't matter what hardware you have or how much time you have. That's what we would like to have, but you can't have it. So how many bits of security do you get with AES 128? You get 128 or close to it. It's pretty good. There is no shortcut of any significance. You pretty much have to try all the keys, so you get 128 bits of security. All right, how long should an RSA key be to be considered safe enough for normal encryption? Yep, 2048 is the current recommendation. And by 2030, we're supposed to move to 3072. It takes a lot longer to use the bigger you make the key, so you don't really want to waste your time by getting too big, but 2048 is currently recommended. All right, so what cost is intentionally large to make Ethereum mining more secure? Ethereum is memory hard. It takes a lot of RAM to mine Ethereum, and the idea was then you wouldn't have one nation have a huge advantage over other nations. All right. So, let's take a 10-minute break. I'll stop.